In 2018, Kīlauea volcano erupted over a cubic kilometer of basalt so rapidly it caused the Caldera floor to drop up to 500 meters. It did that in a number of dozens of discrete collapse events that all generated magnitude 5 plus earthquakes. That was not unusual. What is unprecedented is the near-field seismic and geodetic data that were collected that allow us to gain great insights into collapse mechanics. Basic idea is pretty well understood. Magma was flowing out to the eruption site, depressurizing the magma chamber. This led to an increase in the shear stress acting on the ring fault. That stress led to, as we know now, both creep and microseismicity along the ring fault. Ultimately, the stress level reached a critical threshold, and this magnitude 5 very long period earthquake propagated around the entire ring fault, causing about 5 meters of collapse and repressurizing the magma chamber. So if we look at near-field extra-caldera sites, these are ones sitting on the rim of the caldera, we see inflation, deflation cycles coincident with the collapse events. Notice the scale here for the two sites sitting on the caldera block are 10 meters here. So these sites dropped up to about 5 meters per event and also exhibited many meters of intercollapse subsidence. You see the spatial pattern of inflation here. Microseismicity was concentrated on the newly formed part of the ring fault, and quite interestingly, the rate of microseismicity, just the rate of accumulation of events, is actually quite proportional to the rate of subsidence of the site Cal S sitting on the downgoing block, which really supports the idea that fault creep is a dominant factor between collapse events. We also notice that there's a tremendous variability in the seismicity in the immediate lead-up, the last 15 minutes or so, to the collapses, in which the rate of seismicity, the A value in the Gutenberg-Richter distribution, and the B value change. The B value changing in a way, we get larger earthquakes as the preponderance of larger earthquakes as the collapse approached, and we think that meant that individual small VT events became more likely to break out. So all this suggests a model with a frictionally strengthening fault for the most part. That explains the interseismic subsidence, but localized asperities that nucleate VT events that ultimately break out, causing the large earthquakes. The difficulty has been that we have not developed yet a friction law that is consistent with both the intercollapse creep and the very rapid onset 5-meter drops. One new observation that may be helpful in this is feature tracking from videos, which is in a poster by Josh Crozier showing that unlike the co-collapse displacements, which appear to be pretty spatially uniform, the intercollapse subsidence is spatially variable, indicating either broad shear zone or perhaps buried faults in the subsurface. And we think understanding this may be key to giving insights into the ring fault mechanics. Thank you.